So hi everybody. Today I'll be starting a new chapter, new chapter that will be circular motion. So up till now we're discussing the linear motion. Now we'll be discussing the circular motion. So suppose this is some circle and this is the center of the circle. Oh, the thing is suppose a car starts from here. This is considered as a point one from which it starts, and it reaches here at the point two. Suppose this is point two, so it traveled like this direction from one to two. So suppose during this time it traveled a angle, as it is the center of the circle. So suppose it traveled the time taken is, suppose delta t is the time from which it traveled from point 1 to point 2, and the path it followed, that is this path. And suppose delta theta is the angle that this car moved. So here we have in linear motion we are having the linear velocity, but like here we have angular velocity. Um, so in angular velocity what we measure is like this uh, this delta theta and this time. So what we have, delta theta over delta t, means it traveled, suppose this particle moved from point 1 to point 2, so whatever angle it moved, that will be delta theta, and the time taken by it, that is suppose delta t, so this will be delta t, so this will be omega, that is what, this is the angular velocity. Now the thing is that this delta theta will be in radian, means uh, yeah, radian. So the unit for this will be this omega. The unit for this omega angular velocity will be radian per second. Now we discussed this thing a lot of times, like in this situation when we make delta t tending to zero. It's not zero, but it's very much near to zero. So in that case, we can convert this delta theta over delta t as d theta over dt. Means here delta t is so small that it can be, it's not zero, but it's near to zero. So that small distance we take it as differential element, so means this it's a d theta and it's a dt, differential angle and differential time. So like what this will be, instantaneous, means this is for any particular instant. Instantaneous angular velocity. So this omega is what, this is your omega, this angular velocity omega is this one, that is around this center, you can say. So suppose like suppose let us suppose like particle take n revolutions, you can say n revolutions it makes in 1 second. If like it is given that n revolutions this particle make in 1 second, so what would be the angular velocity? So as we know that the arc of this circumference of this, what it would be, that is 2 pi uh, so suppose it makes n revolutions in 1 second, so what would be the omega? So like in one revolution what happens, like in one revolution what would be the angle travel, like it moves from here to here. Suppose this is your circle and it started from here, it started from here and again it came back here. So what in one revolution what angle it moved, that would be 2 pi angle it moved. So what in n revolution how much angle it will move, that will be 2 pi into n. Like in second revolution, think about it, in second revolution, like this is the first revolution, it traveled 2 pi, in second revolution it will travel 2 pi into 2, in third revolution it will be 2 pi into 3. So in nth revolution what will be the angle travel, that will be 2 pi n. So it will be 2 pi n, and in what time it took, that is 1 second. So what will be the omega? Omega will be equal to 2 pi n, means angular velocity is 2 pi n. There is one word that is time period. Uh, Time period. So like what is time period? If someone asks you what would be the time period, so like or if someone tells you that this is the time period of so what time period is, that is time taken to complete one revolution. So like here what it would be, or leave it. It depends on the situation. So if someone tells you like it take n revolutions in 1 second, so this would be the angular velocity in that case. So so like in linear motion, what we heard about the acceleration and deceleration we studied. So like in circular motion, we have what is called as angular acceleration. Angular acceleration or angular deceleration, both are there. So suppose this is your circle and this is the center of the circle. Suppose this is your initial point, means this is at time t1. Suppose this is the angular velocity, you can say here, this is the time t1, this is at position at time t1, this is position at time t2. Sorry, it's t2. This is position at time t1, this is position at time t2. So here here what I saw, like here the angular velocity, like this is the angular velocity, like angular velocity is omega 1, and what we saw that here when it is at this point at time t2, the angular velocity in this direction, that is omega 2. Like in previous scenario, the whole of the angular velocity was same, but here like this angular, like at this point of time, it was having an angular velocity of omega 1, and at this point of time its angular velocity is omega 2. So like what angular acceleration is? So like we can say like the thing is that vector we are going to use it because it's a vector quantity, and angular velocity is also vector quantity. So we can say like omega 2 minus omega 1 over t2 minus t1, because, or in other words, we can say like delta omega over delta t. Now same thing as delta t tending to 0, alpha is equal to d omega over dt, because same thing I told you earlier also. So this is what? This will be the instantaneous angular acceleration. Like omega, I told you what omega was, that was d theta over dt. So like here we have like this calculus part that you will come across in your math section, but like when we are going to do like here, when we are going to do again d omega over dt, so it will be d square theta over dt square it will become. Okay, so we can write it like this also, d square theta over dt square. Now like let's see the directions of this angular velocity and angular acceleration. So like as I told you that angular velocity is also vector quantity and angular acceleration, that is also a vector quantity. So like suppose remember this thing, actually there is one right hand rule, like suppose this is your motion, like motion is like this, it's the center, this one is the axis, this one is the axis of rotation. Suppose it is rotating with like this with angular velocity omega. So like how to find out this direction of vector, angular velocity vector? So like you can see here, like here the direction is what? Anti-clockwise. So we have one right hand screw rule. So like when you are going to, but it's difficult to explain it without or you can say take your uh, right hand and rotate your fingers, put it on the disc you can say, or put it on this put it at the center of the ring, and you do one thing, rotate your fingers uh, in the direction of angular velocity, means in anti-clockwise direction you can say. So your thumb will show the direction of angular velocity vector. So here it will be like this. This will be the direction of angular velocity vector. If you're uh, like this one, suppose this is the circular motion and this is the axis of rotation. Now the thing is that at this time the uh, angular velocity is in this direction, that is you can say in clockwise direction. This is the axis of rotation. So in this case, the direction of angular velocity will be, when you are going to rotate your use your right hand rule, and when you are going to rotate your uh, fingers in the direction of angular velocity, so your thumb will show the direction of angular velocity vector. This will be right this time, this will be this one. Now here we discussed what would be the direction of the angular velocity vector when it is anti-clockwise direction, when it is clockwise direction. So now take a look into the angular acceleration vector. So like suppose this is the axis of rotation. This is the axis of rotation. And suppose your disk is rotating in this direction, means that is anti-clockwise. The thing is here, it is accelerating. Means its angular velocity is increasing. So then you can say like, you can see like angular velocity is increasing here. So the direction of this, like here, what would be the angular velocity vector? So this will be the angular velocity vector. This would be the angular velocity vector. So like when it is accelerating, so you can say like the direction of the angular acceleration vector will be similar to the direction of angular velocity vector. When your disk or something like this circular motion is anti-clockwise, or you can say it's accelerating, the angular acceleration is accelerating, you can say. So the direction of angular velocity vector will be the direction of will be similar to the direction of the direction of angular acceleration will be similar to the direction of angular velocity. Okay, now in this scenario, what's happening here? It's deaccelerating. What deaccelerating means? It's like you can see it like direction is same. It is anti-clockwise. But the thing is here, like here, angular velocity is decreasing. It's decreasing. Like here, what would be the direction of angular velocity vector? It will be the same like this here. This would be the direction of uh, angular velocity vector. But what would be the direction of angular acceleration vector? In case of deceleration, the direction of angular acceleration will be opposite to the direction of angular velocity. So it will be like this, because the thing is here it is deaccelerating. It is deaccelerating. It's a very important, because the thing is that the direction, you have to remember the direction, like how to find out the direction of the angular velocity vector and angular acceleration vector. So that you have to keep in mind, like how to find it out. So like acceleration and deceleration, clockwise movement and anti-clockwise movement, these matters. So like you can use right hand rule also for finding out the directions of this angular velocity and angular acceleration. So like in this way you can find it out, like when it is accelerating, so the direction of angular acceleration will be similar to direction of angular velocity. When it is deaccelerating, the direction of angular acceleration will be opposite to the direction of angular velocity. Now suppose we will see the relation between linear and angular. Like linear parameters like linear velocity, linear acceleration we have, and we have one angular velocity, angular acceleration we have. So we will see the relation between them. So like suppose like suppose it's a circular path. Suppose this is your circular path. The thing is that like the particle started from here and ended here. The path it took, that is this much. And suppose this circumference is what much? Suppose delta s. Suppose delta theta, like it's a starting point, you can say from point this to point this it moved. And suppose this is delta theta angle it moved, and suppose the radius of this circle is r. So like we know that angle is equal to arc over radius. So like what is angle here? Like here we have delta theta is the angle. What is arc? That is delta s. And what is radius? That is r. Or we can write it like delta s is equal to r delta theta. Do one thing, that we are going to divide this both sides by delta t. So it will become delta s over delta t is equal to r delta theta over delta t. Now what is delta s over delta t? What is delta s over delta t? That is velocity. That is linear velocity. Like here angular velocity is around this axis, but like when someone is, like you might have seen, like if you are traveling from here to here with some velocity, you can say v velocity, that's a constant velocity you are traveling from here to here. So same thing is happening here. this particle is traveling from point 1 to point 2, and from this path it is following this path, and with some, you can say like here it is velocity, here velocity, like with some velocity it is moving. So what is delta S over delta T? That will be the velocity. That's a linear velocity. That is what? Distance upon time. Distance upon time. And what we have here is delta theta over delta t. And what delta theta over delta t is? That is angular velocity. So this is the relation between linear velocity and angular velocity. But it shows like this is your path, this is a circular path, and suppose some particle is moving with velocity v, and in that case its angular velocity is omega, means it is moving here. Here also its velocity is v, and when we are going to see it here, here also its angular velocity is omega. When it is here, here also its velocity is v, angular velocity is omega. Here also its velocity is v, angular velocity is omega. So this is what relation? It's like v is equal to omega into r. That's relation used, widely used in most of the questions. Like you have to remember this thing. Now what we are going to do is like we are going to differentiate it like dv over dt. So like what it will become, d omega over dt. And like earlier we already studied like what is dv over dt. What is dv over dt? That is what? Acceleration. So like here, what's happening here, like, and what is d omega over dt? That is angular acceleration. So what we can write, like a tangential r alpha. Alpha we saw a few minutes back only. At is equal to r alpha. This is an other relation, you can see. Now here we are saying that at, like here the moment is like this. Suppose the particle is here initially with some velocity v1, you can say, and suppose this is omega 1 at this point. So v1 is equal to what? V1 is equal to r omega 1, you can say. This is the relation. So like here what, like suppose like it's this velocity is increasing. Like if it goes to point this one, like here the velocity, suppose it's v2, and it means that v2 is greater than v1, and suppose here it is omega 2, omega 2. Suppose here when it reaches here, this is suppose v3, and angular velocity is omega 3. The thing is that v3 is greater than v2 is greater than v1. It means this velocity is increasing. w3 is greater than w2 is greater than w1. Means this velocity is increasing. It's if it's an angular velocity is also increasing. So like when some velocity is increasing, that is means it is accelerating. So you can see here like linear velocity is increasing. So some tangential acceleration might be here, a t in this direction, a t in this direction. You can say here also a t, that is a t means a tangential, a t. Why we wrote it tangential? Because the thing is acting at a tangential angle, you can say, like here. So this is AT, this is what is AT, and like this omega is also increasing, so angular acceleration is there. What the angular acceleration is? That is alpha, because angular acceleration is also increasing. So like this AT is equal to R alpha. It means if we know the tangential acceleration, we can find out the angular acceleration, and if we know the angular acceleration, we can find out the tangential acceleration. But the thing is that, like here what was happening in this scenario, you can say, in this scenario you can say, what's happening was, like here you can see, like our velocity v was constant, our velocity v was constant, you can see here. Our omega was same, our omega was same. So here what was happening, like at is equal to 0. The thing is that here the velocity is constant and alpha will also be 0, because like you can see here, like omega is same, omega is same, omega is same, means it's uniform motion, you can say. Uniform means throughout it's same, like velocity is also same throughout the circle, angular velocity is also same throughout the circle. So this type of motion, you can say it's a uniform motion, or uniform circular motion, you can say. Because the thing is that our velocity is constant, as well as omega angular velocity is constant. So like you have to remember this thing, like this, if you know, like v is equal to omega into r. So by the help of this, if you know angular velocity, we can find out this velocity. That's, you can say like this. Let me show you in a clear way. So like I told you, v is equal to r into omega, and at is equal to r into alpha. This is your circular motion. So if you know, like here, this angular velocity, we know if it's omega, then, and it's a constant, you can say it's a constant, means throughout the circular motion it's a constant angular velocity, you can say. It's tangent to this circle, you can say. So here it is also omega. From this relation you can say it is equal to r into omega. When someone asks you from here, what would be the tangential, you can say, remember this thing, it's, this is r into omega. But the thing is, here you can see, like this is constant angular velocity, so means alpha is equal to what? 0, means angular acceleration is 0, because velocity is not increasing, it's constant. So like here, this tangential acceleration is also 0, because here you can see, here it's omega r, here also it's omega r, here also it's omega r. So like in this case, it's like it's tangential also, it's 0. Like when body is moving with constant velocity, linear velocity, its acceleration is 0. Now suppose this is your center, and like here the velocity is omega 1, and this radius of this circle is r. So like here it will be r omega 1. By this relation you can say, by this relationship you can say, v what would be the tangential velocity? This will be r omega 1. Here here like suppose angular velocity becomes omega 2, radius is r, so it will be r omega 2. And the thing is that this omega and suppose here what would be the tangential part? Suppose here angular velocity is omega 3, so it will be r omega 3. The thing is here like omega 3 is greater than omega 2 is greater than omega 1, you can say. So here it is constantly increasing, so some angular acceleration is there. That's why this you can say, like as you can see here, like omega 3 is greater than omega 2 is greater than omega 1, so this r omega 3 is also greater than r omega 2 is also greater than r omega 1. So this linear velocity is also increasing. So if it's increasing, there might be some acceleration is there, and what acceleration it will be? Like this will be a tangential, a tangential, a tangential. And what suppose like omega 2, omega 3, omega 1, it's increasing. So like suppose if it's alpha, then at is equal to what? R alpha, r alpha, at is equal to what? R alpha. So like these two relations, like this relation you can say, by the help of this relation you can find out the relationship between tangential acceleration and linear acceleration, and this one is for linear velocity and angular velocity. So like in circular motion you have to remember that how to find out the direction of angular acceleration vector and angular velocity vector, and at this relation like v is equal to omega r, at is equal to r alpha. So I think that's enough for today, and we'll go into more detail in circular motion in our future classes, or next class you can say. That's all for today. Thank you.